So anyway, thank you very much for coming. Thank you for all my colleagues, my speakers that will come after me, and also for the panelists from the other projects, and of course all the audience. I hope you liked what we are going to show you. This is the final event of the project. It's been 4.5 long years, with a relatively dramatic moment, as you know, in COVID period. But anyway, now here I must say I'm very happy with the outcome of the project, but there will be time for congratulations at the end. So for the ones that doesn't know the project, a brief facts about the project. This is it was supposed to be a 4-year project, 40 months project, but then it was extended due to COVID. It's 7.4 billion budget project, and there's 14 partners from 11 countries, plus the 18 linked third parties of EFG. And we have geoscientific SMEs, like and academic, both from mining and from robotics, NGOs and governmental institutions. Okay, I can skip this because if you are here, you know the problems with raw materials in Europe. And just a couple of quotations from the call. So we're addressing this call, new solution for sustainable production of raw materials. And concretely from the call text, I took this text, which is was expressing the need for very innovative and sustainable raw materials production solution to bring the next digital generation to the raw materials field. And that's what basically we have done. So we want to bring high technology to the raw material, and to change a little bit the way that the mining is seen. This is like a dirty and very heavy field, which is, but if you bring technology, robotics in this case, and many other technologies, we can provide this transformational effect. Okay. And of course, we want to make a different kind of mining which is more sustainable, and that can be more socially acceptable. We target 3 main scenarios: so abandoned mines, small and high-grade mineral deposits, and ultra depth. And all these 3 scenarios are scenarios that are not, in our vision, not mineable with classical technology, or not economical viable, let's say. So that's where we want to put robots and technology. We want to send robots where the man cannot go, or is not because it's very dangerous, or it is not economic, let's say. Okay, so this is the concept that we had in mind at the time of writing the proposal. So we want to have robot modules. This is a modular robot, modular technology. So these modules would be brought into place via a borehole, for instance, but depending on the access, on the way to access the mining site. They would self-assemble. This is a low TRLL project. It's a research project. So there's some of the things are at a conceptual level. So like step 2, for instance. So they would self-assemble. We've been working on that in simulation and also with prototype to form a fully functional robot. And when the robot is fully functional, it will start mining the ore using specialized sensing device to sense the ore, and specialized production device. They will produce a slurry. This is supposed to work both in water and in dry environment, but the water environment is the one that is most suitable, because we will produce a slurry that then is pumped out from the mine with classical technology. Okay, and because they are modular, they would self-reconfigure on the job, which means that in case of some failure or different needs, they would change their physical configuration to cope with different situations, failures or different needs. So these are the specific objective: construct a fully functional modular robot miner capable of performing selective mining. And I want to stress the selective mining part, because as you see, the robot itself is the most visible part, and everybody always fix their attention to the robot, but the robot is just one of the components. We have many other things inside and outside the robot. Validate the key function to the lab, not only lab. So we went a little bit beyond TRL4, because we've been on field testing, and design and studied also the mining ecosystem, which means that we are not only focused on the technology, but also on the impact that this technology would have in the whole in the whole system, as an overall mining system. And then use these toys and these gadgets to study future challenges. Okay, so more concretely, we've been working on robotics, as I said, selective mining, and mining ecosystem. I will go very fast on these three topics because my colleagues after me will show the results more in detail. So we've been working on locomotion in different means, in harsh environment with innovative locomotion means, autonomy navigation, classical of robotics, self-assembly and reconfiguration, as I said, and also self-awareness. So we've been producing 3 different prototypes for testing different things. So this is the big one, RM1. RM2 is a lab toy, and RM3 it's another scale model to test sensors. What you don't see, well, this is easy because you see it. What you don't see is the artificial intelligence, okay? So because this is software. So I want just to spend 1 minute describing what we working on as far as self-awareness. Self-awareness means that the machine, the robot, is capable of reasoning about itself, its performances, and being capable of understanding which is the functionalities it needs to perform the mission, what is that he can do, and how he can reconfigure, or how he can change its configuration to address the needs. And it is almost philosophical. It's like who I am, what am I doing the right thing, and how I can improve. And this means software and hardware. So this is a very quick example. It's a log file, so you don't really see it. Okay, but what I'm showing you here is that in the picture above, there's one module trying to do mining, and it realizes that it has not enough force to actually dig the rock. So what it does is call for another module to get together, and they form the robot that's below. That are 3 modules: the production module and 2 locomotion modules, and the 3 of them can perform the mining. And this reconfiguration is done by the robot itself, because it knows that it's not performing well. It reasons about the capabilities needed and what is around, what it can do, and decide that by adding another module, it can comply with the mission it is supposed to perform. And everything is done by the robot itself, but reasoning about, as I said before, about its capabilities and the mission needs. Okay, also, I want to also highlight that we are in the borderline between mining and robotics. So for us, this is a very big machine. It's a huge robot. You don't see these big machines, or not as many. But on the mining side, we are almost a toy. This is a very small mining machine, even too small. Actually, the comment that we say from mining industry is always that it is too small. Okay, so it's very huge machine for us, very big robot, but very small mining machine, and we are in that border. Okay, this is about robotics, about selective mining. Let me go a bit quicker because there's a presentation about that. We've been working on perception devices and production tools. So we have mid-range geophysical sensors, mineralogical sensors, and we've been working on production tools. The one that you see is the final product, but we've been doing different prototype and simulation, numerical simulation to get to the point. And finally, as far as mining ecosystem, we've been working on different levels: mining design, mining strategies, geological modeling, how to integrate the information that we have a priori that we can have, and the information that is being produced by all the sensors that the robot has, to integrate everything in real time to help the robot taking decision. And if this is the case, also an operator can overview and take decision for the robot. We've been also studying the impact about micro and macroeconomics that this system would have, when it is profitable and when not. And we also have made an inventory of relevant deposits, which means which deposits in Europe would be suitable for adopting this technology. There's many of them. And last thing I want to talk to you about is about the impact. Of course, this is a technology, but which is the impact? So, of course, as I said in the introduction, the whole purpose of the project is to provide Europe with the new technology, new exploitation scenarios for mining. I forgot about that. And we want to bring high technology, the digital innovation in mining industry, and this is also have the we think that can have a positive impact also on new generation, and in particular to fill the gender gap, because if you see a field as a high-tech industry and as high-tech field, maybe we can encourage young people and also women to start working on that field, to change a little bit the image of the field. Of course, we want to have environmental benefits. We do different mining, low impact, no dewatering the mine if it is flooded, no human in the mine, less waste, and less impact on the on ground. We can also imagine also to enable small-scale mining and artisanal mining, which means that this kind of machine are several orders of magnitude less complex and less costly than the normal mining machine, and that might empower a new small companies, let's say familiar company or artisanal company or small communities can perform mining, not just the big companies. Of course, increase the domestic supply of raw materials for Europe. And finally, this technology, we believe it is also suitable for other fields, like extraterrestrial mining, which is a very hot topic lately, ISRU, in situ resource utilization for mining asteroids or moons or whatever. And also, maybe Jussi will mention later, all the technology we tested in the robot is rated to 1,000 meters of depth, so it can go underwater and do mining on the sea bottom up to a certain limit. So, and that's about the project. We have our social networks, and now it's time for my colleagues to go a little bit more in depth on the technology. Thank you. Any question? Maybe take question. We take question later. Now it's Goraz.
Yeah.
Okay.
Thanks. Thank you, Claudio, for this nice introduction about the project. First, let me introduce myself. I'm Goran Žibrat from Geological Survey of Slovenia, and I will tell you a few words about our vision of the mine of the future. You are probably very familiar with this, but I will just quickly repeat it. So why do we need mining? So first thing, global demand for raw materials and energy is increasing, and also the demand per capita is increasing. So there are more people on the earth, and each one is consuming more resources, so we have double exponential growth at the moment. A variety of resources we use today has increased, so we actually are using the whole periodic table of elements. Recycling, unfortunately, cannot meet the demands. Some commodities are even not recyclable here, and we cannot substitute raw materials, non-renewable raw materials with renewable ones, because it's impossible. Even green technologies use significant amount of raw materials. So mining, whether we like or not, will still play a crucial part to maintain society as it is and maintain the current living standards. What is not grown, it must be mined. So mining, but only a few, like the most accessible and rich deposits have already been mined out. There are very few high-grade reserves left on the surface, but a lot of low-grade reserves. So as we can see in this picture, the average ore grade which are mining is constantly decreasing. Coupled with ever increasing demand for raw materials, the mining strategy of the mining companies are to grow, to get bigger and larger, because the costs are lower. As we see on this graph, if we have a larger production, annual production rates, means decreased cost per ton in underground or open cut mining. So now we have big machines, big open pits, big environmental impacts, big everything. But there will be no depletion of resources. The only question is what will be the price of their mining. So it's clear that mining of the future will also need to occur in areas which are not suitable for humans to go there and which are not suitable with current mining technology, like ultra deep environments, ocean floor, and similar. So mining there will be costly, for sure. But using robots in such environment can have several advantages. So first of all, because there will be no humans in the mine, we can drastically decrease the costs for assuring healthy, safety conditions there. So we don't need to cool the mine, we don't need to pump the water out and so on, which can decrease the costs. So robots can also work around the clock, so they don't need breaks, they don't need to travel to the surface, they don't need holidays. That is, again, a big advantage compared to the humans. Mining can, of course, also in scale. So these current mining machines are adapted to the human size and go big, but robots can go also smaller. So there is no need for certain scale range, for certain size of the machines. Because of this, mining can occur more selectively. It generates much less waste and has much less environmental impact. If we use a robot in mines, we need less people to operate the mine, and we have better working conditions. And yes. And what if we change the paradigm? So, like having in mind, like this very small sulfidic vein. What if we can really precisely extract this vein? Because such deposits might not be very interesting for conventional mining techniques. But if we can economically mine this and have like a lot of smaller mines instead of big mines, yes, we can have the advantage, and in this way we can unlock really a lot of resources and reserves. So mining is for sure the thing which should be done by the machines, not by humans. And I will quote the Agent Smith: "Never send a human to do a machine's job," and then we can proceed to our vision of the mine of the future. So our mine of the future is completely automated. No humans are needed underground. Human interventions are needed, but can be done remotely on a very high level control. Machines are modular, can self-assembly, self-disassembly, self-repair, can replace the worn-out parts. Machines are able to sense their environments, so to distinguish between ore and waste, and are able to make decisions accordingly. Minerals are extracted very selectively, very precisely in all three directions, not only left, right, forward, backwards, but also up and down. Mine layouts are complex, fractal-like, so they follow the natural mineralization. They don't dig into the parts where it's not necessary, as it is today. Mining, there is much less need for the mining infrastructure. Mining machines can start digging from the surface, reach the deposit, start excavating the ore. Also, mineral separation and ore beneficiation is being done underground with in situ backfilling, so we have much less waste on the surface. Only ore concentrate is transported, or even maybe we can also merge downstream industry like metal processing or metallurgy to this mining system of the future. And of course, when we have this system, it can operate also in every kind of environment we have in the space. So, but there are many technological challenges to reach this stage. I will not dig into the details, but I will only mention the most significant ones. The first, of course, is energy supply, whether to have batteries, we have some future fusion or whatever reactors, or it have a cable, is attached to the cable. Then motoric and locomotion, how will the robot move? With legs or with tracks, with wheels or with some other means of propulsion. Sensing and awareness, so the machines will need to sense the environment. And also in very harsh conditions with zero visibility, in slurry or Cutting the rock is another challenge. It consumes enormous amount of energy, and you need also to assure the back force. Then ore transportation, big data handling, communications between the robots, between the robot and humans, human-machine interaction, decision-making, robustness and resistance, and so on. So the man who moves the mountain begin by carrying away the small stones. So there are various solutions which tend to reach this vision of the mine of the future with small steps. Right now, there is a lot of things done regarding automatization of certain tasks in mines and remote control of the machines with coexistence of humans and machines. So mainly in the excavation phase, which is the most dangerous place in the mine, a lot of work has been done regarding to sensors and to merge all of this information into virtual reality environments, which can help operators of these machines to do their job better. I named some of them. There are many more of them, like VAMOS project, UNESMIN, Sandvik auto mine system, Soil Machine Dynamics did a lot of work related to mining of the ocean floor. There is Korean CRISO underwater mining machines, these spiders which collect the nodules, and many more of them. But also ROBOMINERS, yeah, is also, we think it's a big step forward towards our vision of the mine of the future. So I will finish with this general presentation, with this general vision of the mine of the future. But I will now have 4 more slides to present you some less technical aspects of the ROBOMINERS project, because in further presentation you will see the very technical stuff. So we are doing a lot of geology here, mainly in work package 5. So we were doing a lot of determination about the most suitable ROBOMINERS mining scenarios, as Claudia already said. We defined 3 of them, but not only 3, there are many more, but we identified these 3 to be the most suitable, like operation, like mining in abandoned or active mine with known resources, which are currently not interesting with conventional mining. So this is very interesting because all infrastructure is there, and it's much easier to start to doing the first test, the first commercial missions there. Ultra depth, this is Kuiperschiefer example. So Kuiperschiefer is a copper mineralization, which is about 1 kilometer, 1.5 kilometer deep, but it stretches really in the vast area. And it's very thin, like 0.5 meter to 1 meter. But the resources there are really, really large in Europe. And we found this to be very interesting for ROBOMINERS. And small deposits, can you imagine this sulfidic vein? I showed the picture, soil deposits, which are really not interesting for conventional mining techniques. We also created a database. Claudia already mentioned it. We also did a visioning. If we have this kind of robot, we have this kind of machine, how the whole ecosystem would look like. And I believe Steve Henley will talk about it a bit later, so I will not go in deep here. We did a lot of thinking, how to proceed, road mapping, how to proceed further, what steps do we need to reach our vision, to have first commercial operations to 2030, and to have the whole system developed until 2050. Where do we get funding, and so on. And we also did a preparation for pilots at higher TLR levels. We also did some job regarding, as Claudia mentioned, regarding the economics, the environmental impact, the social impact, policy impacts. With macroeconomic investigation, we thinking about the general economic situation, like for general deposits, these 3 deposits we were mentioning before. We saw that critical parameters are price of the ore, obviously, productivity, uptime, and initial investment costs for the infrastructure. And then in the next step, we did very detailed into 3 actual deposits with actual data, and determine what if we use the robotic system there, what are the advantages, disadvantages, or what are the critical points. We again identified the critical parameters for lead zinc. For one deposit in Portugal is cost of the borehole, And for other two scenarios, copper, silver, and epithermal gold are the cost, actually price of the ore. So to conclude, we determined the main advantages of this robotic mining are the selective ability to perform selective extraction in all kind of size, all kind of scales. The next advantage is minimal surface and underground infrastructure needed, unmanned underground operation, and shorter time to assess the deposit compared to conventional mining. So thank you very much for your attention. I'll finish this with the miner Prometheus installation from Slovenia. It's ROBOMINERS, but it's not moving. It's only for artistic. Thank you. Yeah.
So good morning, everyone. My name is Georgia Stasi. I work at the Geological Survey of Belgium, and today I will give you an overview of the sensors that we developed in the project. So it's a very quick presentation. If you have further questions, you can follow up. We can follow up later. So since the beginning of ROBOMINERS, we thought that the robot would be evolving in different environments throughout all its mining journey. And for this reason, we figured two main scenarios. The first one being a dry or partially flooded mine, so with clear water, with a rock face that is visible, a good ore-host rock contrast, and where the mined rock can easily be transported eventually via a belt system. The second scenario is a fully flooded mine, no clear water, so we are in an opaque medium. It's difficult to access deposit or gallery. And the main transported rock is transported by a slurry. So it's a slurry transported by a pipe under high pressure. So in these two types of scenarios, we try to develop sensors that could apply in both cases. The first one that I'm going to present you is tactile mapping. That is some whiskers that you see here in all the figures that were developed by Caltech University and that were mounted on the RM3 platform. So the RM3 platform will be further explained later by Asko in his presentation. And these sensors, basically, they can be used in mines where there's no light, so we cannot have no use for visual sensors. And what they do is that they use like whiskers for cats. So they touch either the mine wall or the bottom of the floor, and they create a SLAM-based mapping. So we can visualize the obstacles and the mines of the wall. We can use this type of sensors where conventional sensors do not work and there are few or no reliable landmarks. Then, once we touched all the mine walls, we want to actually know what's on them. So one of the means that we can use is hyperspectral mapping. We use this type of technology in our latest field trials in Međica mine in Slovenia. It's a MVT deposit, so lead zinc mine in dolomites. And as you can see in this lower right image, you cannot discernate the dolomites from the sphalerite. So it looks like it's a bunch of the same things. So if we apply hyperspectral measurements using ultraviolet light, as you see in the top left image, we can actually track the sphalerite very well because it pops out with these nice red colors. So here, one of the main challenges we overcome was the miniaturization of the hyperspectral cameras and the coupling of the two cameras to have a broader range and to have a larger amount of spectral information acquired. And these type of techniques can be used to map the wall of a very complex ore. Then once we know what's on the surface of the wall mine, we want to know as well what's inside, so how far these veins are developing inside the wall mine. And to do that, we thought about two different types of application with ERT, so electric tomography. And here in this first case, you see the lab application of piston-based electrodes that then we mounted on the RM1 platform. And why did we use piston? Because we wanted to have some models where the electrodes could be autonomous, so we could retract them when we were moving and having some drilling operation, and then we could re-extract when we wanted to have actual measurements. Here you see them in a classic linear setup, but in the robot they are displaced all along the body. So they are using an irregular electrode spacing for 3D environmental mapping. So the main challenge for that as well is that we cannot dig holes in the wall mine to insert the electrodes, so we had to rely on the pressure that is applied from the piston themselves and the slurry that is surrounding the robots. And so this is applied for the scenarios where we are in a flooded underground mine. If we are on a dry mine, and we can use a different application, and using just the front of the robot, so instead of the drilling head, we can mount a sensing head. And here you see in the small figure over here, this is a very small prototype. It's only 20 centimeters in diameter. And what you see mounted here is some electrodes that are coupled with some graphite on the front to have a good contact with the wall face, because we are in a dry environment, so we need to verify that actually the electrodes are touching the wall. And this is used to have detail mapping for ore following. So with this technique, as you can see in this image, here the yellow part is the sphalerite that I was mentioning before, and the white part is the dolomites. When we apply this technique, you can see that we can go in depth. So this image that you see here is basically a horizontal cut inside the rock. And so you can see the extension of the vein in a couple of centimeters in depth. Of course, this depth of penetration is limited by the spacing of the electrodes. So if we apply a bigger spacing, we can go more in depth. Then, just to continue, another technique that we applied as well for chemical mapping of the mine wall is the LIBS, so laser-induced breakdown spectroscopy. In this case, we did remote LIBS. Normally, you see this setup in the lab with a very nice samples under the laser. In this case, we mounted our laser on a tripod with a motor that is scanning the entire wall. And here you see the example. In visible light, we had this nice geometry with galena, sphalerite, and dolomite. And this is the result of the scan of the wall. So here, the main point is that we can install this head on the robot. We can do a scanning of the entire gallery that we have, because we just need the rock face to be visible. The wall can be irregular, so we don't need to have some polished section. And we can really well discern the contrast between the elements. Then, so this is for what we call LIBS mapping dry, and then you will see why, because we also did LIBS in wet environments. So we use the LIBS in a piping system from when we are actually extracting the slurry. The slurry is transported via pipe, and the pipe is passing through this nice pipe that has some windows where we shoot with the laser inside, and we do real-time slurry analysis. So it's a control of the ore that we are extracting. So we can actually detect if we keep extracting the mineralization or if we are extracting more sterile host rock. So it's a matter of control as well. The nicest innovation in this is that we can run the analysis on the slurry that is passing under high pressure, and with the several sizes of debris and abrasive material, doesn't matter, so we can still run the analysis in any condition. And then, as last, just an overview of all the sensors that we installed on the RM1 system. So, as you can see here, they are coming back the piston-mounted electrodes, so there are two in the front. This is at the closed system. When they open the direction, like two antennas of insects. Then we have another couple here mounted on the belly and here in the back as well. Then what else? We have the reflectance sensors on the bottom of the first module to check a bit on the slurry and on the composition of the bottom floor. And then, as you can see here along the way, we have the lip slurry analysis system. And this is it for the sensors. It was a very quick overview. So if you have a question, just pop up them later. Thank you.
Okay, thank you. Hello, everyone. My name is Michael Berner. I'm working at the University of Leoben, and our part in this project was we were not in the beginning, sorry. Our part in this project was the production tool, and today I want to briefly present you all the tasks related to it. So just to give you a quick overview, we have like several production tools which are probably feasible or need to be analyzed in the beginning, which might be capable of be used in the future and future mining robots. And for that, we made this huge applicability assessment in the beginning, like great theoretical studies with numerical simulations of excavation processes, just to define some application limits and minimum requirements for production tool systems and for the robots, of course. And out of that, some conceptual developments have been created for all kinds of different scenarios, for mining soft rock, medium hard and hard rock, mining, tunneling, and exploration. And the second major part was the development and the testing of a production tool suitable for our prototype. So that's basically the two main tasks. One are the theoretical simulations and assessment of all the futuristic and potential production tools in the future for mining hard rock in a continuous way, probably. And the second one is developing a suitable excavation tool system for our robot prototype. And that's where the real challenge was, because on the one hand, we needed a production tool which was able to excavate rock in a more or less continuous way. And on the other hand, we have like this limitations of the robot. It is very lightweight, it has very low amount of power, and that means the maximum strength of the rock to be excavated could be only really low. So that's where the challenges began. And yeah, as you can see here, we decided on a part face cutter head because it was more or less feasible within the time range, and it helped us to implement a tool which could continuously excavate soft rock, but with that continuous excavation, we were able to transport the material with our slurry production system and analyze it in stream. Now I want to quickly show you what we did with this production tool. In the beginning, we had to, of course, test it to find the limitations and to set the boundaries and the minimum requirements for the tamper team, for the structural development of the robot. And we created this full-scale cutter head test rig to test various rock strengths, measured the cutting torques and the cutting forces, and of course did a performance assessment just to get a feeling of what is possible with it and our robot. So this was the test rig in the lab. We tested several rock strengths from 16 to 30 MPa and 1.60 and 70 MPa of UCS. The sample was mounted here in the front in the sample cage. Cutter head here is rotated, powered by a hydraulic power pack with approximate power of 18 kilowatts. And how did it work? We had this thrust cylinder in the back, pushed it inside the rock sample. Once the cutter head is inside the rock rotating, we pulled the sleeve cylinder and pulled the probe from left to right, just to imitate the cutting motion. All of this had been, the measurements had all been done with some low-cost Arduino systems, the torque and the force measurements, and of course we had some novel dust emission suppression system with this old-school vacuum cleaner. And what tests did we do? We had 3 different rock strengths to be tested because we knew already that the maximum UCS to be excavated must be really low, and we concentrated more or less on like region 20 to 30 MPa of rock strength, and we had real oil shale samples from this open pit test mine, because at that point we already knew that we might test it in the Estonian oil shale mine, and that's why we tested those also. So we can see here a video. This was one of the last tests where we tested the oil shale. Only a very small part of the cutter head is in contact with the material, but we clearly see that it is no problem. It is no problem to excavate this oil shale material here. But on the other hand, as we can already see here in this part, we have all kinds of different grain sizes which need to be transported away. And this can be better seen here, which gave us the limitations or the boundary conditions for our slurry transport system. That you can see here some, because of the brittleness and the rock is really fragile, our grain size distribution was very irregular and uneven. And after that, we could do some kind of a performance evaluation. I just want to say what Claudio mentioned earlier, that we're here trying to combine like robotics and mining, and conventional mining machines, they have high productivity. They can mine hard rock. That's not the way where we wanted to go. This is not about productivity. This is about testing different technologies together in combination, and we did not promise any new production tool here. That's why we'll come to that. Numbers here, we have like estimated excavation rates about 1 cubic meter per hour for oil shale, which is in mining terms next to nothing, but in our scale, it's quite a lot, and this gives us a hint for the future that we need some different alternative production tools for mining hard rock. Could be alternative systems, drill and blast, just to be able to go into this hard rock directions for special scenarios. And in our case here, we did all these tests, and we knew for our robot the maximum UCS is around 40 MPa, which is really soft rock material, and that's one reason why we decided to test our robot in Rakvere in Estonia in this oil shale mine mine. And I want to show you those 2 test videos where we tested the rock cutting capabilities. One was the submerged cutting to test the material transport, and the other one is the dry cutting test here, and you can see very easily that excavation of oil shale was no problem with that machine. Yeah, that's it from my side, from the production tool side, and I'm happy to answer any questions. Thank you.
Okay, thank you. Hi, everybody. I'm Asko Ristolainen from the Tallinn University of Technology. And I will be talking about the robotic platforms that were developed within the ROBOMINERS project. So in the project, we had 1 full-scale prototype developed by the team in Tampere. And we had 2 small-scale prototypes, the RM2 and RM3, that were developed in Madrid and in Tallinn. And the main purpose for these smaller prototypes was to investigate the technologies then later we did transferred to the full-scale prototype. So I will start off by the small-scale prototype, the RM3. So our research questions, starting with this, were 2. How can we locomote in environments which properties we really well do not know? And secondly, how can we perceive the environment, and how can we localize ourselves and map the environment which is sensory deprived, meaning that we can't really use conventional sensors like cameras or lidars. So what can we do for that? And we basically ended up having this sort of robot. For locomotion, we decided to go with screw locomotion due to its simplicity and robustness. And for sensing, we were investigating bio-inspired sensors, mainly the tactile whiskers on the robot. And we combined them, of course, with the conventional sensors to investigate their performance against the state of the art. Now, I will go and show you the developments over the phase of the project. So we developed the screw locomotion in lab scale experiments and continuously develop it further to be applied on the field. So we developed dynamic and kinematic models for these kind of robots to be later applied on the RM1 prototype that the Tampere team was developing. And this was the first step to go towards developing robots that can go around in mines, because we needed to first have the locomotion part done, and then we could add sensors to that platform and investigate how we can sense the environment. Now, continuing. So with this platform, we were mainly focusing on the mapping and localization. And, mapping and localization. So this robot it was like a hedgehog. It had a lot of these whiskers all around the robot. And by having those whiskers, you can create a point cloud just by touching things on the ground and on the walls. So you can create like a map, which is kind of limited view, but it's okay because we are inside a mine. There's limited space that you can travel to. And we used then these sensors to try to localize ourselves. Secondly, we also developed autonomy, mainly wall following. Mines have walls, so you can follow the walls to get to the ore or to localize yourself. And we also developed algorithms for navigation purposes just by using these tactile sensors. Now, the second prototype, the RM2, was developed in Madrid, and its sole purpose was to study reconfigurability. So Claudio in the beginning was mentioning that there might be a scenario where we lower the robots down through a borehole and have them self-assemble. So the Madrid team was focusing on the reconfigurability aspect of the robotics. So for that, they developed a docking mechanism with 5 degrees of freedom with a soft continuum arm. And then they used these modules to study robots' self-assembly capabilities. And here you can see some pictures of that with a production tool mock-up and the coupling mechanism in here. So shortly about the modules, they can be reconfigured with different locomotion submodules. You can add different sensors to these modules. And also the docking mechanism, you can fix other modules to that, or production tool, or other sensors. And all of these modules were self-reliant, meaning that they had onboard computational capabilities, onboard batteries, and so on. So it was a lab-scale prototype, so the weight was just below 5 kilos. Now you can see a couple of videos. So these modules can couple with each other even when they're not aligned in the mine, so it just has to be in the proximity. This is the advantage of using these soft coupling mechanisms. So, and you can also pick up tools from the ground or add different sensors in front of the robot. Now comes the interesting part, where we actually integrate all of the technologies we have developed throughout the project. So the team in Tampere was in charge of that. So their team was building a full-scale prototype, as you can see down in here. It comprised of screw locomotion that was investigated by our team, the production tool, slurry transportation mechanisms by RCI and RBINs, and some facts about the robot. So the robot itself was about 5 meters long with a small diameter to be able to make small tunnels, and the weight was, as it was said earlier, rather small, 1.3 tons only. Now the neat aspect of this robot is that it used water hydraulics, meaning that it was completely safe for the environment, and actually the water that was found in the mine was used to power the robot. And then the robot also had an online system for detecting what was digged out with the robot, and also all of the components of this robot were waterproof, meaning that it could do underwater operations as well. Same slide again, all of the different aspects that George already described. I will show some videos now. More details first. The robot itself is not just a robot. You need to have an ecosystem to run this robot. And as it was using water pressure, we needed to have some auxiliary systems in addition. For example, the high pressure power pack to power the cylinders and the motors on the robot, then different backup systems, communication centrals, and so on. And you will see in the next slide how the whole system was set up in the test site. Also, a network was set up for the system to monitor all of the systems online while the robot was operating. In total, there were 48 nodes running on the robot, so meaning that there was no single computer that could break down and break the robot. And then this was all custom built for this prototype. On the video in here, you can see how the whole system was set up on field. So, yep. We had control stations in the field with some auxiliary systems, water tank, power generator to power the high pressure power pack. And we actually had a section of a mine just for our purposes for a whole month in Rakvere. So during the demo, all of the systems were controlled remotely. No operators needed to stand next to the robot. Tampere team had a special container built up for control. In field, we had a leap system a little bit further back from the robot, as you can see in here. And the robot was tested in a test pit in half submerged conditions to allow the slurry to be transported from the robot. Now, the robot uses screw locomotion, as you can see in here. You can see that it can actually carry this 1.4 ton robot. And the advantage of the screws is that they're very robust. You have very few moving parts that can break. And secondly, the robot also have the screws able to move in and out from the robot's body. So in case we are inside the mine or have excavated a path with the robot, we can actually use these screws to fix ourselves to the walls to have more support for drilling. And finally, as Michael was already showing, we did experiments with the production tool, first in dry conditions to visually inspect how the tool was working, and then in submerged conditions to allow also the slurry transportation and online analysis what was digged out. So That was very shortly about all the developments. There is much more to talk about, but we can do that later after the session. And finally, few of publications that are already out there that you can find, but there are many more to come after the end of the project. So thank you.
Okay, thanks. Right. Okay. Don't need the pointer, just. Okay. Thank you. Just to introduce myself, Steve Henley. I'm a member of the 4D Coders team. We're what they call a group of natural persons. We started the project based in the UK, but during the project we've evolved into a Europe-wide team from the far east to the far west of Europe. The most far-flung members of the team are in Bulgaria and in the north of Scotland. But we still work together effectively. Most of the team got together yesterday and are here today. And because of the time, I can't condense all that we've done over the last 4.5 years into just a few minutes. So I'll concentrate on the central aspects. There are other parts that we have done which I won't be talking about, particularly completing the engineering work on the slurry collection system, and also some of the database work, which was vital, but is not very spectacular to look at. Okay, so what we were looking at particularly was the mine development strategy. Many conventional methods of underground mining, and although generally less wasteful and environmentally damaging than surface open pit mining, even so, mechanization means that the openings tend to be developed in waste rock, and so large volumes of waste rock are also produced from conventional underground mines, and especially from the small and high-grade deposits, just to allow access of people and large-scale mining equipment. So this is the key issue that we've been addressing in ROBOMINERS, not only smaller and more intelligent mining equipment, but also adopting a new approach to mine development. So one of the things that we looked at was the modelling approach for the geology and the mine openings, and with particular attention to the need to transfer the model knowledge to the mining robots. We very early decided that the conventional cuboid block modelling was not going to be appropriate, and developed tetrahedral block modelling, which integrates well with the geophysical and engineering simulations, the geophysical exploration that Georgia was talking about, and with engineering finite element modelling. It also lends itself to function-based modelling for efficient loading into the robot memories. We then addressed the mine design and mine layout. Conventional mining using rectilinear tunnels and drives involves a lot of extraction of waste rock. So we took our inspiration from biological systems, and in particular looking at trace fossils of feeding patterns of worms and other burrowing creatures. And that gives us new ideas for mining strategies. Of course, every deposit is different, so any strategy adopted must be adaptable. It must evolve as a biological system evolves. It could probably be condensed into one phrase: we can learn from worms. So we focused on two that seemed particularly useful, the fractal tree and the greedy algorithm. This shows what the fractal tree mine layout looks like. It's not particularly adaptable. However, the greedy algorithm, it does what it says. It takes out the mineral, the high-grade mineral. It is selective mining, ultimate selective mining. We used public domain data from the closed Lachine mine. Now, let's see how we can get this started. We've used public domain data from the closed Lachine zinc mine in Ireland, and we've simulated how this algorithm might work in 2 or 3 dimensions. Is that going to work? Yeah. So the grey-green are the existing surveyed mine workings. The coloured section is drill hole data. And then using short-range sensors, these perception devices, the robot can start developing the mine, and it'll then continue automatically to extract the ore deposit, mining a minimum of waste. Okay, here it looks like it's gone wrong, but it soon finds its way back. That's in 2 dimensions, but the algorithm works just as well in 3 dimensions. And so this is how it has produced a 3-dimensional mine layout. The graphics are different, but the algorithm is the same. And it produces a network of mine workings that are completely unlike any conventional mine. So that's how it's extracted the minerals from a massive deposit. Okay. And then we moved on to integrate the geological mine model with the engineering. So we're combining the geological and mine layout with the engineering of the robot itself. And we can simulate this. Don't try to read the captions on there because we've speeded up the video. Kaloyan developed that video for us, and it took rather too long. So we're running it fast. And that shows how the robot actually moves in the mine. This is simulating what the engineer would see in the control room of a ROBOMINERS mine. So it's not just a simulation of how a mine might be developed, but it's what you might see on the screen of a mine using ROBOMINERS. The robot there is a modified RM3, as Asko was talking about. It's a little robot. It's not the RM1 full size. The terrain again is the Lachine mine. The tunnels that it's working through are the actual Lachine tunnels, so they're full-scale tunnels for big mining equipment and people. The data are held in the robot, so if it runs into a dead end and has to retrace its steps, or if it develops a fault, then it has a memory of everywhere it's been, and it can reverse precisely to its starting point. Okay. Thank you. That was a quick overview.
Okay, so I think was the last of the presentations. We have some minutes for some questions and from the audience, both here and online. Let me just fetch my Zoom. So if anybody online would like to ask a question, you can just write on the chat. But for the moment, do we have any question for any of the speakers here? Many of them.
So thank you for the presentation. I'm really happy to see the achievement of the project after 2 years that I left the project, actually. So this is really, really nice. And I have one question for Asko and one from Steve. So the one for Asko is just, I know it's the beginning of every junction between the models and the modules, sorry. But did you consider underwater environment with slurry around, for example? Because you show us like the soft connections. But I was wondering if you just thought about the environment.
Yeah, we did that. Actually, our own prototype is also waterproof. Although for the sake of the project, because it's our only prototype, we haven't taken it underwater yet. But we actually have other applications planned for that project, and one of them is mapping the coastal areas to map both what is down there and also the motion of water with these similar sensors to map coastal erosions and things like that. So we have like other applications for that, but yeah, for the sake of the work and research we do, we didn't take it underwater yet.
Thank you. And my other one for Steve. Sorry, yeah. I love your model, like it's really nice now. But I was wondering, just did you consider the stability of the rocks when you are doing the model with the geo-inspired galleries?
Yeah, that is one of the things that I didn't show. That another of our team members, Colin Morrish, is he was a former mines inspector in Saskatchewan, Canada. He knows a lot about mine safety, and he did some modeling using finite boundary element methods, to look at the potential stability, and that is something that can be integrated in with the robot movement parameters. There's a lot that I didn't show, and that's one of the things.
Thank you very much, and again, congrats.
Hello, my name is Kostas Botsialas. I'm representing the Mastermind project here. Really impressive results. Congratulations to all of you. Really hard work and really inspired work. There was a very interesting slide about the scale between mining and robotics. And that was the prototype is somewhere in between, too small for mining, too big for robotics. And that's true. I mean, the scale in real mining is huge. But on the other side, how easy could it be for a prototype of this kind to be reproduced in many, let's say, if someone has a fleet of 1,000 of them?
Yeah, that's one of the concepts. Maybe I didn't mention, because what we envision is to have a colony of this. But this is not one mining machine. This is a colony of tens, hundreds, or they say the number, mining underground like a ant colony. So how easy to reproduce? It depends on the money. Of course, the first prototype is always very expensive, but then if you start mass production, I don't know, usually maybe you can answer. I think very easy. No, we have the blueprints, and it's a matter of buying new parts.
If I answer. So, Jussi Aaltonen from Tampere University. So I would say it's easy, because we have the infrastructure. It's developed, and we have the blueprints of the machine. So it's just reproducing a lot of machines and connecting them to that one infrastructure. Of course, all of them are prototypes still, but anyhow, the kind of basic work has been done, and it will also work same way with as it worked with one robot, it will work with 100 robots or 150 robots or so on.
Okay, thank you. And talking about not just the quantity, but also about the size, how easy could be this to be 10 times bigger?
Yeah, it's not easy. It's possible, and considering the future applications, we have to think about scaling it bigger. But we probably have to think about also scaling it down a little bit. Because it's not so that one size fits all. If we want to take large-scale mining operations, we need definitely larger machines. But then there are also those possibilities for really small-scale mining operations and artisanal mining and so on.
One comment on upscaling. Actually, the big mining machines, big rotators, long wall, they are robots already. What we are missing there is maintenance. So this is also where we could live with this small cutting unit. I wasn't tired to say 10 kilos of something is not mining, not unless it's diamonds.
Ah, I didn't see them.
But it was part of a pilot vehicle where many cool technologies were developed and tested.
May I also add something? Our intention at the very beginning was not to compete with big open pit mining. So this is intention was to explore really very new and very innovative mining system. So these machines will never compete with big open cut.
There's a few questions from the chat, from the online. One is for Steve. Steve, does your simulation estimate the productivity per day at Lishin?
I guess that it could. It's not something that we've explored yet. It's, yeah, there's no reason why it shouldn't.
Mm-hmm. Okay, thank you. So next question is from Enrico. Enrico, Tech Scout and Business Angel. I am mining and drilling. Is mining and or drilling equipment taking part in the project in any way? I think it's from Michael.
Yes, of course. As you've seen in the presentation, we tested one prototype, one small-scale production tool, and the other equipment has been analyzed and assessed theoretically, all different kinds of excavation tools for exploration, tunneling, and mining, of course. So, yes.
Another question from Enrico. It seems the robot can perform well in a straight line. What about performance when it has to change course, steer, to open its way through the mine? Maybe I can take that. If I remember correctly, the boom can steer 15 degrees, left or right.
Tunnel can turn 15 degrees.
Yes, and then which is the turning radius? So I don't remember the figure. So it can steer, of course, the turning angle.
Turning radius is something like the length of the robot.
The length of the robot, so 5 meters.
And in any direction, so it can go down, up, and both sides.
Okay, perfect, thank you. And, sorry. Okay, no more questions from online. Any other question from the audience? Steve, one comment?
Answer to that one about recording the production rate.
Mm-hmm.
Of course, all the information is held in the database,
Mm-hmm.
so it's just a matter of generating a new report from the database.
Yes. Yeah. Okay. So if there are no more questions, 1 second.
Maybe a word about the production. With economic studies, we determined that if the robot will excavate like half cubic meters per hour, we are on the safe side regarding the economy, because we estimated the cost of the machine to be 100,000 euros. So it's very small investment, and if it can dig like half cubic meters per hour, it will be perfect.
Okay, so this is the end of this part, and congratulations to all the speakers because we are very well in time, so we're on schedule. Thank you very much for your attention. Now that we have a coffee, and then there will be the panel discussion. Thank you very much, and let's have a coffee.
Thank you. So thank you again for being available for this second part of this session about the future of mining. I would say not only in Europe, but across the world. We have now a panel discussion with representatives of other EU-funded projects, also looking to novel technologies. And let me first introduce the guests that we have today. First, we have José António. José António is coming, Ortiz, sorry, from the, he's a mining engineer. He's coming from the Madrid School of Mines and Energy. Nice. You have more than 20 years of experience. This is what it says in the website. And you have been authoring more than 200 scientific publications on and involved in more than 70 research projects. So this is a lot. You are also responsible for the DG EcoQuery Horizon 2020 clustering activities, right?
Yes.
So thanks a lot, Jose, for joining. We also have Philip.
Thanks to you.
Philip is coming from the Leoben University, also a mining engineer. He has a huge experience on all things connected to mining operations, and that includes from the geotechnical into the more operational areas of drilling, blasting, etc. And he's also the coordinator of Illumination, a project that is there, and the subtitle is The Future of Mining. So let's stay there, don't run away, because we'll be talking about this very soon. Costas. Costas is on my left side. He's an engineering geologist. He's coming from the Aurora Geo Consulting, okay? And of course, you have a PhD and also in geology and hydrogeology. And you are representing the Aurora Geo project.
No, the Mastermind project. Aurora Geo is one of the partners of the project.
Okay. You have been in Mastermind and TerraVision then?
Yes.
Okay. Thank you for joining, Costas.
My pleasure.
And Guillermo. Guillermo on my right hand is also a mining engineer. So I believe we are so far the only two geologists. He's coming from the Research and Development Department at Citra Subterra, which, by the way, does not say this is a European company? Spanish?
It's from Spain, yeah. It's just recently acquired that French company.
Thank you. And you have been contributed to projects in mining, open pit and underground, and you serve as technical manager for the DIGIT project. So thank you. And finally, but not least, we also have Richard. Richard is not representing Horizon ongoing project, but he's the CEO of a spin-off of a company that was basically uptaking the results of another EU-funded project, UNEXMIN, if I remember well, that created a robot. So you will tell us about how is now that company going and the efforts of picking up research results and doing something that is completely different from that. So thank you all for joining. And I will start with the first question to Philip. I'm using my mobile phone because you see this is a very sophisticated approach. And to Philip, the illumination goal is to make underground mining operations environmentally friendly. This is said in your website. So assuming this is feasible, can you please give us some examples how this will be more friendly in the future?
Yeah, well, I think we have to go back to the entire package of this project, and I think of many of the other projects. So what we are doing in illumination is we're developing a couple of different sensors for many different purposes in underground mining. So we're talking from environmental monitoring, we're going to geotechnical monitoring, we're going to battery maintenance, we're going to additive manufacturing. So we cover a huge diversity and a huge portfolio of different sensors and different developments. But the environmental friendly part comes into play when we utilize these sensors and when we utilize the information of those sensors. So if we combine the data in a meaningful way, if we can come up with new mining systems, with new mining layouts, if we can observe changes in the rock mass, observe changes in the in the effects of what we are doing in a better way, then of course all the operation gets more efficient and more environmentally sustainable and friendly. And especially with those technologies that we are deploying in rock mass stability on the one hand side, but we're also talking about measurement while drilling on drill rigs, analysis while drilling on drill rigs. So similarly to what has been presented in ROBOMINERS today. And with the combination of those, it's a TRL 3 to 5 project, so I cannot say we can do it, but we're sure to be able to do a much better extraction planning, a much better or much higher yield in accordance to the deposit model, and that's where we believe that this environmental friendly boost in environmental friendliness, that's the right word, comes from.
And you are also testing that in any sites?
So the project is pretty large with 19 partners from all over Europe, just 6 countries, but still all over Europe, north, east, south, west. And we're having 5 pilot sites in that project. So 4 of them are actual mining, 3 of them are real mining sites. One of them is more it's a tailing dam facility, so there's also a very huge impact on the environmental impact. And the 5th one is a major machine manufacturer. And so in the mining sites, we are testing those technologies which are, of course, important for mining. So these are rock bolts who can measure, so intelligent rock bolts, as we call them. So we want to deploy a sensor on every single rock bolt. Nowadays, you have sensors on, 2,000 euro sensors on just a couple of rock bolts in the mine or extensometers. What we want to do is we want to develop sensors we are developing sensors for every single rock bolt, which come at almost no additional cost, but having much more information there. That would be for underground. As I said, also measurement while drilling, analysis while drilling would be for underground. And for the tailing dam stability, of course, there we deploy lots of artificial intelligence and machine learning. The sensors in this specific tailing dam are already in place. I think there are more than 3,000, Christoph, correct me if I'm wrong, more than 3,000 sensors in place. But what the project is doing, or what the partners in the project are doing, is getting a better picture from those sensors by using machine learning and artificial intelligence tools in order to predict, hopefully not failure, but mitigation measures and
Okay, that's
everything that's associated to that.
Okay, thank you, Philip. And quoting again the website, Guillermo, this one is for you. DIGIT is the acronym to Human-Centered Internet of Things Platform for the Sustainable Digital Mine of the Future, right?
Yeah.
That's a long word. So one question, because when I see that, is that platform also capable of enabling, let's say, more safer and sustainable mining? How do you see that?
Yes, of course.
Oh.
That could be the main outcome of the project, but indeed, DIGIT project aggregates a lot of technologies and a lot of disciplines. For example, the consortium has 16 partners, and just Subterra is the geologists and geotechnical specialists, and this is a mining project, let's say. But it's good to have a global view how other partners can work in a mining environment and integrate their technologies there. For example, we can enhance the efficiency by developing predictive maintenance operations using IA system, using big data analysis. Of course, we can increase the security and the safety of the workers, because we have developing some smart garments, which are, for example, some vests and some headphones with very specific technology. I'm not an expert on this kind of robotics, maybe Tau partners are, but they are also developing some predictive maintenance equipment for their underground operation systems. By doing this, I think we can enhance the security of the workers, but not also with this safety vest, but also by analyzing all the sensors on the gases, developing real-time modeling of these fluid dynamics, etc. So, of course, I think I know the description is quite large, but it is true indeed.
And these, like the vest example that you gave, this is already being tested? Is something?
Yes, yes, we have some prototypes. We have the vest is connected with they have pulse rate and other kind of sensor. We have a wristband which is already working at the site in Marini Marmi in Italy. Sorry.
Okay.
We have the smart helmet, let's say, which is going to be tested in Finland. So these are on-field applications, real applications right now, but of course prototypes, but we have good outcomes of this.
Okay, thank you so much, Guillermo. And Kostas, Mastermind. I like the name, huh? Like the Mastermind, it reminds me of the game Mastermind, but it's a good word change. You are building competitive and low-impact mining industry in Europe. And how is this possible? Again, technology, I guess?
Not only that.
Okay.
Technology is the one, let's say, lever. It's the one way to do it. The other way to do it is to make people to accept, to inform people and to feel people that mining is not something bad for the communities. You see, in Europe we're pretty spoiled because for centuries we're having the raw materials from other areas of the globe, using them in order for us to develop. But now we see that this way is not very sustainable, and we have a lot of, let's say, a lot of opposition, and a lot of competitors as well, China, for example, or other parts of the world. So yes, technology is a very useful way. In Mastermind, we're going to use a whole set of technologies which are trying to cover all aspects of mining. So our ambition is to create a set of suites that will try to create digital twins of each aspect of the mine. And in order, all this information and actions that should be taken are going to be centralized and going to be shown in a metaverse, which is called MetaMine. But in one of these suites that we're going to use, this is called Our Mine. And in this suite, we're going to try to establish, a two-way communication with the local communities about mining, about the process, and what is achieved every day, what are the plans for the future, for the area. So in this way, we are trying to not reduce the position, but to make people to feel safer, that mining is as we said, as was shown in the beginning, if we want to continue to have this kind of society, we have to have mining. There's no other way. Or even if we want to transform it, then we have to use mining again. So one of our modules, which is called Our Mine, and is going to use technologies in order to bring closer people from the societies within the mining industry, is one of the cornerstones of the
impressive.
Of Mastermind.
I must say I'm amazed by the fact that you are combining very sophisticated, let's say, future approaches like the metaverse and digital twins, and on the other hand, you are also talking with people.
Yes, because it's about people.
So it's
at the end of the day.
Yeah. Just let me say that the questions are also open to the audience after this first round of questions. So I guess many people are already wondering about that. So, José, now, about DG Eco Query. Again, quoting the website, it's implementing digitalized, automatic, and real-time process control for aggregated queries. So I guess the difference between a query and a mine, especially an open pit mine, is not so big. And I'm wondering, how can you explain how these technologies will also translate to improved public acceptance and also lower environmental impact?
Yes, as the name of the project or the acronym says, we are digitalizing aggregate quarries from the extraction process by the rock mass characterization, blasting, and also all the processes that take place in the treatment plant. Okay. So we are installing sensors, tools. We are developing artificial intelligence algorithms, and with the idea, with the goal of optimize the production, but also the energy consumption, and and also to focus on social acceptance. As an example we have installed dust sensors made by us in a quarry, and we are also considering or taking into account meteorological information to know the dust produced by, well, not the natural dust, and the dust produced inside the quarry to apply this for the water consumption, for the watering of the open pit. Yeah. Okay, so that would be an example. We are also developing artificial intelligence algorithms to forecast the production, but also the energy consumption in order to reduce the electricity or the fuel consumption and all these things. So that would be applied to reduce emissions in general, but also within the quarry. And also we are organizing many activities for general people, for local communities. In fact, yesterday in Madrid we had within the scientific week, which is called which is organized in many universities of Spain. We have more than 100 people talking about not only quarries, but the benefits of mining activities and the applications of these minerals and these rocks in our life.
Okay, interesting. You were talking about the dust sensors. These
Yes.
are real time?
Yes, they are real-time sensors, yes.
Okay, because I see there is a lot of information.
Yes.
I mean, of
Well,
work being developed, aligned, right?
Philip is the leader of Illumination, but is also within the partner of the Eco Quarry. So, I think all the things that we are developing are connected and are
indeed interesting.
Yeah.
Because again, from my experience, it seems that public opposition to mining is bigger than public opposition to quarrying. At least in Portugal.
Well,
people is against lithium mines, but not against what they think are lithium existing quarries. So, but we'll be back to this very, very soon. Just let me first ask Richard about his experience from UNEXMIN Georobotics. That's the name of the company. Yes. That was a spin-off of the UNEXMIN project. And I wonder, as CEO of the company, do you have any advice for these researchers and also for the people from these projects how to uptake the results of all this investment made by the European Union in technologies?
Yeah, so thank you for the question. So practically what we are doing currently and what was the actual goal of the project, actually it was not only one project but two projects. To developing a technology that is able to explore and monitor flooded mines and flooded underground mines, was to introduce a kind of mining ecosystem that was already mentioned by Claudio and even Gorange today, where we are maintaining and checking flooded autonomous mining systems. That is for the future, and the UNEXMIN and UNEXAP projects, and currently UNEXMIN Georobotics is taking the first step of this robotic technology. And Gorange mentioned a lot of aspects of these mining ecosystems. What is the future of that? What kind of technologies are not developed yet? What should be concentrated on? And which type of even software or hardware developments could be done in the next if we are considering 2050, then in the next 30 years or almost 30 years, then I could say for all the researchers that are thinking on developing mining systems is not concentrate only on the actual mining technology that can mine it, but also all the other aspects that were mentioned by Goreft. So with artificial intelligence, with all the sensing, with all the perception, with all the navigational possibilities and navigational problems that can occur in underwater environments. And meanwhile, you can adapt all of these technologies to other places. So not only in the Earth, not only underwater, but maybe in 2050, we can thinking on space exploration and space mining. So this is what I can advise for even a young researcher to develop technology, is to check those aspects of the mining which is not ready yet and try to concentrate on one thing. So based on our experience, we had 2 projects, and even that 2 projects was not enough to finalize all the technologies that it needed for flooded underground exploration. So there will be a bunch of steps till we can finalize this kind of autonomous underwater mining ecosystems.
Okay, thank you, Richard. Because we are talking about artificial intelligence, I was again looking to the notes I had from the projects, and I have a question for you both. Because you are talking about sensors and basically real-time monitoring devices, do you think that there is a risk from the technological development side, because things are evolving fast, and some of the devices that you are now developing won't be feasible or usable in a couple of years, so these artificial intelligence algorithms won't basically paying attention to that or will be replacing that. Philip, what do you think? Is that something that worries you?
I think it worries me more from the social acceptance perspective, or from the public perception perspective. So as an example, I've been sitting on the train yesterday by a pure chance with one guy from the Austrian mining authorities, and we've been talking about that topic about when we have thousands of sensors deployed in the mine and we promise to measure something specific, how do the authorities then, for example, deal with an error in that messages or in these measurements, or if one of the values is deviating from the normal. And we always need to have somebody who is cleverly interpreting the data and providing that info, or filtering the information in a way that is meaningful and useful. Because when you just have the measurements, you might very quickly run into the risk that somebody says, okay, there's one value red, now close down the entire mine. Probably that's a bit exaggerated, but that might happen. So you need to explain the data in a good way, and that's why I'm thinking from the public perception that might be a bit of a tricky thing generally to install so many sensors without explanation. And the second part that also stems from recent discussions is, and I have it here on my notes as well, it's kind of don't digitize for the sake of digitalization. And that's the huge difference between the 2 projects that we are representing. So the illumination projects dealing with large mining companies, which much more engineering power, with a company that is owning 2, 3, 4 different mines who see this overarching connection between the mines and between the KPIs that they want to measure and so on. Quarries are structured in a completely different way. In some of the quarries, you have 2 truck drivers, 1 excavator driver, and 1 guy who's running the processing plant. And they do not have this engineering power. They do not have all the background information to sufficiently run that development or to implement it in the most meaningful way. And there I see more the problem than the technology itself. That it would be there, but you need to use it in a meaningful way.
Okay, that's a very good question to you.
Yeah, so well, in quarries, what we have seen is that there is no many data, and now we are taking real-time data to to optimize all the activities in the quarries. So what I think is that we are putting the basis for the quarries in the future. Of course, technology develops very fast, but we are using machine learning. So as far as we get more data, all these services and this methodology will will have more efficient application to queries. And what I think is that also some of the services can be extrapolated or can be used also in other type of mining activities. Yeah. So.
But I was wondering, because you said as we get more data, and you are both working with digital twins. You also have digital twins, right?
Yes, sure.
So you need huge amounts of data, I guess, right?
Yes, that's right. And
how can you collect it? And Costas, please.
It depends on the scale. It depends on the operation. As Philip said, in big mining companies now, it's very easy to update data.
Yes,
there are many,
of course.
There are many different techniques. Techniques are changing every 4 or 5 years. I mean, we are geologists. Remember how we were doing mapping 15 years ago, which is not that far, 15 years ago, and how we're doing mapping now. What we were using by that time was very sophisticated, one notebook and one compass, and that's it, and a map. Okay, today is totally different. Today it's totally different. So we in big scale, we are acquiring a lot of data in a small amount of time, and then the people who are working in the mine or the ecosystem around the mine, they are sitting in front of the data, they're thinking, okay, now what? What we're going to do? And they remember, I mean, someone is geologist, even if he or she is having a PhD or a mining engineer or whatever, doesn't mean that you're an expert in database compilation or in GIS or in geodatabases or all this stuff. You need to have some expertise. Okay, so these type of projects, they are creating ways to fuse data from different sources in order to obtain decisions in a quicker way, or in a more effective way. Okay, so I found this I mean, Mastermind or Digit or the other projects a way that in order to consolidate data and to create meaningful decisions, meaningful outcomes from this data in a real time, not real time, in a reasonable time.
Yes,
okay.
not exactly real.
Not real. Yeah.
Okay, and I wonder, you also have problems with getting all that data, right?
Yes, yes, of course. I can say for sure that the main problem of the project was all the sensor stuff, because you have to install 1 or 2 or 3 or whatever sensors you want in each mine, but one of the objectives was that the sensors have to be low capex sensors, and this could be a problem because, for example, when you install a chip, let's say chip sensor in a big open pit or in an underground quarry, the sensor is going to fail because the environmental conditions are really tough. So you are installing a low capex sensor, but you have to replace it in 3 months. So how can you deal with it? Well, this is one of the options of the project.
Of course.
Sorry? Okay. Okay. So the other problem is to connect all these sensors in just one platform, because the idea is to have one decision support system which compile all the information together. So you have different sensors in different mines, and you have to install infrastructure and some communication protocols that are interconnected all together, and this is quite complicated. But we are managing that. We have all the sensors, almost all the sensors connected to the same platform, and we are receiving real-time data, which is the main objective of the project, and we are using this data for digital twins and also the decision support system, etc.
And in your case, you also have the people. I mean, the guys that are working down there,
yes, of
providing
course.
more data.
Yes, we are receiving the localization of the workers, the health condition of the workers.
Yeah.
So.
And speaking of workers, and I'll be opening the discussions to the audience right away. One last question to you, Richard, because you also mentioned that geologists today are not exactly like geologists, at least in my time, with the hammer and the compass. And I wonder, is it easy for you to get the people that you need to work with? I mean, because you don't necessarily look for geologists or to mining engineers, right?
Yes, practically it's complex. I'm also a geologist, actually.
Okay,
because
so
this side
is the left side. Okay. My left, you're right.
Yes, so practically what we are doing currently and what we did in the last few years during the development was fusing the robotic engineers, all the engineers from software and hardware point of view, and tried to train those kind of geologists or geoscientists who can deal with the actual data that we collected.
In-house.
In-house.
Okay.
Yes. Yes, and that's something which is really tricky. I would say not directly in-house, because we were a consortium, and of course right now we are a company. But everything is based on a consortium, and everything is based on the same partners or almost the same partners during the projects. And because of the complexity of the robotic system we had, we needed to find a good way to post-process everything and to see the results, and even to communicate these results to the customers. So, and we also dealing with big data, or a kind of big data. So what we are collecting is several terabytes of data during a day, and that should be checked, that should be validated, that should be somehow integrated to a final model. And for that we needed a lot of learning, even from data processing point of view and from geological point of view and robotic point of view.
Yeah.
So practically our experts are kind of fusing a lot of information and a lot of knowledge from robotic point of view, from artificial intelligence point of view, and also from geological point of view.
Yeah.
And I'm envisioning that this is a kind of end result of all the development that is going on currently, because in the end a commercial geologist will be not enough, or the commercial geological knowledge will be not enough to be able to process all this data. So we need to be able to program something, so to just write some codes, and of course meanwhile to fuse everything that was based on the real geological information.
That's a challenge, eh? I wonder. Okay, so let's see if we have questions from the audience. I guess that you have now, I would say, not a deep understanding of the projects, but at least an idea of what our guests are doing. And Steve, I see that you are raising your hand. Please.
Okay, this actually follows directly from what Richie was just saying. The demographic problem in the industry is that mining engineers and geologists, the average age is increasing. It must be in the 50s now, and within the next 10 years, a large number will be retiring.
In Europe?
In Europe. We're really talking about Europe.
Yeah.
And also the universities, I could speak about the UK universities. There is only one university in the UK now which offers undergraduate courses in mining engineering. And in fact, I think that even that course has ended. And economic geology is considered as a much more general field. They don't teach mining geology. So what we've been doing, this is as a former partner in the UNEXMIN project, we've been supplying UNEXMIN data to universities in England for their postgraduate courses, so that they can use the data, they can become familiar with the robotics methods. So the question that I want to come on to is, how do you see robotics in the future as addressing this demographic problem?
And that's a question for someone specifically, or shall we have...
For the panel. I
think
everyone
for the panel.
will have a comment.
And I will emphasize that both Philippe and Jose, they are coming from universities. So perhaps let's start with you. Okay.
Yeah, what you have said is a really challenge, because well, you said that in UK you have only one undergraduate or it finished. Yeah. In Spain, what we have noticed is a decrease in the number of students that goes to the geology engineering or mining engineering degrees. So, well, it's a problem because geology it's not teach in the schools, in the secondary schools. So at least what we are doing in our university is to go to the schools to present the benefits of geology, the importance of geology, the importance of mining. And well, we are trying to push in that way. Of course, what I think also is that it is important to have a connection with people from telecommunication, engineering, to have to develop this kind of robots and this kind of technology, because we know about rocks, we know about mines, but there's other people. There are other people who knows about the technology, and the combination of these two parts, I think, is the most important thing for the future. Yeah, but it's a challenge for mining and geology and geological degrees. Yes.
Yeah, I think one of the important things is that the students themselves need to be enthused. And it doesn't start at university, it starts at school level.
Yes.
There's a project, it's an EU project, TripGift, which encourages development of virtual field trips for school students.
Yes.
Even if they have no direct access to geology, they can make a virtual field trip online, and they can exchange rock samples.
Yeah, and also the social acceptance what has been mentioned about mining. Yes, well, I want to use my mobile phone. I want to use my car. I want to live in my house. Yes, but this comes from mining. But there's a not very good social acceptance about this, and I think we have to push in this way to say that we have a lot of benefits by using or by extracting minerals and rocks from mines. Yes.
And I noticed
it's also not a purely European problem, that as Victor
exactly
said. There was a recent McKinsey survey of North America and Australia, and it found that in the 15 to 25 year age range, the mineral industry was seen as the least attractive career path.
And I was wondering, because Philip was taking notes, and I know that Leoben is trying to attract students too, and you have been quite successful, right?
Well, I think the question is as old as, at least as old as Agricola has written De Re Metallica, because the first 20 or 30 pages in De Re Metallica is about explaining to the king why raw materials are important. And we're coming back to that question again and again and again, centuries afterwards. But of course, we observed that all over the world, and also recently in the SME journal, so the Society of Mining Engineers in the US, there's a feature article about the perception of the industry towards the graduates and what are the qualifications and whatever. And Vito and I have been working on a qualification framework for mining engineers 3, 4, 5 years ago. So it's recirculated and recirculated. But what I've been taking notes here is three word sentences coming back to your initial assessment about the robots. And I wrote here, robots replace people, robots need people, and robots attract people. Because in the industry, the robot can replace the persons because people cannot go there. We have had this argument today. But also robots need the people to control the robots, the people to analyze the data, as you have been just mentioning. And we are significantly struggling with finding the right people for controlling those robots in the mix between mining, geology, robotization, digitalization, whatever is out there. And finally, and coming back then now really to the question about how to attract people, is I think that also robots attract people, because something that people do not, so the general public does not see, is that exactly what we're talking about here, that's the reality in mining. And mining, well, we always say that mining is dirty and mining is retarded, forgive that word. But in fact, mining is working with state-of-the-art technology. Autonomous driving is a fact in mining. It's not on the road. Drone flying has been firstly used in mining and similar areas. Robots, of course, are used in, well, big assembly halls as well, but not in that sense anywhere else except for mining. And I think that is a message that we also need to bring out, that mining is using state-of-the-art technologies, and we are not those dwarfs with the cape and the hammer and the chisel anymore. And I think that would also attract people, not just because we need the raw materials, but also that we work with cool technology.
That's true. Looking back to history, we have seen the steam engine. It was developed for mining works. Are there more questions? Yes, please. Another question there. Please.
Thank you. I've got a question. I just want to make a quick comment beforehand. Because we've basically seen, if we break down the discussions about reinvigorating mining in Europe, that there are basically two main obstacles. One is public acceptance, and second is the sheer cost of mining. And we've heard that throughout this morning, that the deposits that we have left in Europe are currently very, well, I wouldn't say not economic mineable, but it's difficult mining in terms of making the economics work. So just on the first topic, there was an interesting development over the last couple of years in Germany, where I'm from, where it basically turns out that both in terms of renewable energies and new mining projects, there seems to be strong parallels in terms of public acceptance or public resistance. Everybody agrees that it's necessary. Nobody wants it in front of their house. And the biggest mitigating factor that was cited, both by communities who were basically voicing their concerns, as well by project managers trying to get the projects off the ground, was that a tangible benefit has to stay in the community, which in its most simple form could be some form of economic participation. Because the core criticism that always has been raised is we get the ugly side in front of our doorstep, and the profits go to some investor somewhere else. So, and I know that from working in other parts of the world, that public acceptance dramatically increases as your share in profits increases in the profits. Okay. So that's something just to bear in mind. But the second thing is we don't have any tier 1s or tier 2 deposits left in Europe. So we have to deal with tier 3 deposits at best, which are very difficult economically to make work. So in terms of the technology we're developing, it has not to be only focused on sustainability and optimization. It basically has to drive down mining costs. And I've been working more than 20 years for a big mineral corporation, and whatever project we looked at, whatever technology was brought to us, to our projects, the very first question raised is, how does it help to drive down cost? Does it increase cost or does it drive down cost? If it increases costs, go away. If it drives down cost, tell us more. Okay. So in terms of, and that's a question basically now for the panel, in terms of all the different aspects you're developing, I know from ROBOMINERS that it has at least a potential to minimize mining costs due to its modularity, due to its standardization design, which adapts itself to mass production. So there is a potential long-term benefit or aspect that might be able to drive down cost. Now, in terms of the other projects, how much has been cost reduction and therefore making it actually a tool to make new deposits not only technically but economically feasible as well? How much has that been part of, or is that part of the development of the project briefing?
Thank you for your question. It's a very good one, indeed, because as you said, we knew, I mean, the industry looks to the numbers. So having this connection to reality, I probably will start with you. Have you made that assessment in Mastermind?
Yes, this is one of the key issues that Mastermind is working with. Mastermind is having, as I said, many suites, which are dedicated to different parts of mining. So we have a suite which is called GeoMine, and this suite is mostly related with a safety against geohazards and productivity. So in this suite, there is one module which is called Smart Mine Design. And in this module, we will try to create the best possible mine design in terms of open pit, for example, in order to have the best the optimal slope angle which can be sustainable in terms of stability. And as we know, the steeper the angle is, the bigger the recovery is, but also bigger the risk for a slope failure. So, of course, if we manage to steep the angle as much as possible, then we're going to reduce the costs of taking out the waste, of mining the waste. That is one thing. Another thing, for example, is the water treatment and raw material recovery from water, which is taken out of the mine. So in this case, for example, on the one stage, we will be able to take out raw material, which can be part of the production, and at the same time, the water itself, which will be treated, it will be good enough to reduce again in the whole process. Okay, this is another aspect of reducing the cost.
Sorry, and is it working?
We're just 10 months after the beginning. So
Okay.
I will tell you in 4 years.
Okay, so we will be back to you in 4 years. And I wonder, in your case, is it also possible to reduce costs?
Yeah, I would say that Digit is more focused on enhancing the safety and the security of all the mining process, the work, etc. I can say that Mastermind, that we are also working with Costas, is like the Digit 2 or the second part of this project, and Mastermind is focusing now on this economical aspect. But of course, we want to find some economical aspect in the outcomes of Digit project, but it could be difficult to find this. Maybe, of course, we are trying to use low CapEx sensor, as I said just before, in order to digitalize all the mine works or the mine operations. So maybe, yes, you have to spend some money to do that, but in the end, you are having a global view of the whole mining process just in one decision support system, and maybe this is going to save you some money at the end of the day.
So you haven't made yet an economical analysis of
Not yet, yeah.
Okay. But I wonder, in your case, you have done it, right? Because small quarries, they don't have much money to invest on sensors. Are you crazy? I only have one rig or whatever.
No, we are working on that, but we are in half of way of the project, and we are, for example, as I mentioned, trying to optimize the water consumption in the quarries. We are also installing sensors to detect anomalies in the machinery, and that would benefit because we will have an alarm in order to say, well, you have to stop.
How much it costs?
Well, some thousands euros. So, yeah. So, and also to optimize the explosives that we have to put for blasting, and well, as I mentioned, we are optimizing all the processes from the extraction to the treatment. So, but we haven't done any economic.
Because that can save money.
Yeah,
I mean,
yeah, of course. Yeah, to
blasting
reduce
the energy consumption.
Energy consumption, and yeah,
and of course, and I wonder, in your case, are these devices for monitoring too expensive?
Well, first of all, the direct answer would be we did not do any economic analysis. So we are on a low TRL, so we're developing the technologies. On the other hand, we have had pretty significant discussion with our project evaluator at the last review meeting. I hope he doesn't listen to this panel. Nah, he can listen
online.
He can listen to it because it's an open discussion here. But we have had significant discussion. What is a low-cost sensor? What is low capex? And it will strongly depend on what you want to achieve with that. And we have been discussing about a new Raman probe, for example, that just cost, I think, like 15,000 euros now, and a big Raman probe costs 150 or whatever thousand euros. So it's already 10% or whatever of the original price. So it's a low-cost sensor for the part.
For the value.
For the value, but it's definitely not a low-cost sensor in itself. And so it will strongly depend on the exploitation case that you're having. When it is purely speaking about safety, then, well, safety in the end has no price tag. Of course, there can be there should be a reasonable balance. But the technologies that we are developing to make it very shortly, they are not directly contributing to a cost reduction. Of course, indirectly, as you have been mentioning, we are changing processes in the end, and you need to, or stop angles, or support systems. So we hope that, for example, with the rock bolts that we're developing in the future, we can control the support system much better, and in the end, need to install less steel to get out more copper, kind of, or less shortcut, whatever, because we know much more about the support system with an improved sensor combination. But that is beyond the scope of the project, but that is at least the wish list that we're having, or the thinking that we're having, that this on the long run, of course, increases the economic performance.
Okay,
but there's no direct answer to your question.
Yeah, but Rixi, you are already selling your services to the market, and I'm assuming the industry asks you about costs, right?
Definitely.
So you need to show off, to show to them that you have an added value.
Yeah, so practically what we are doing and what we can offer for the mining companies first is, of course, fasten up the flooded mine reopening. So we can save them one-time money regarding actually the time. Okay. So we can fasten up the mine reopening. It depends on, of course, the mine and, of course, the issues, even with days or weeks or months or half a year or 1 year. It's depending on a lot of things. And the other part is the risk mitigation. So when we are going down, of course, for the mining companies needs to pay some money for the exploration, but in the end, they will have an actual look on the mine structure. They will know how it looks like. They will know which type of damage was taken due to the water income, and even they can start the mitigation in advance. And that's also save an extra time and money, and even direct savings can be happened because, for example, we can measure different water parameters. So when they start to pump out the water from the mine, they will know what type of actual pollutions are in the mine or in the mine water, and what type of treatment should be done. So practically, we were checking the possibilities to adapt this technology for small mines and for bigger mines. Checked the maximum or the overall maximum amount of money we can save for a mine, but of course everything depends on the mine side and the community that they are mining. But practically, we are not making them a continuous cost reduction, but only one time, which can directly fasten up their mine reopening process. And from the other hand, and we realized that in the last I would say 3 or 4 years, when we started to make actual field missions and field works, that the society always wants to see what is down there. And what we can do during our missions is to make live stream on all the data that we are producing during a dive, and all the people who are living there usually visiting the site and visiting the monitors, checking what is going on there. And this is a kind of need from the mining companies currently that we are offering actually, is to have a meeting or have a media coverage on the whole exploration during that 1 or 2 weeks when we are working in the mine, and all the local people can see and ask us, not the mine, but ask that company who are actually making the exploration part and the exploration job in the mine.
Okay, and we are back to public acceptance and stakeholders engagement. Okay, more questions from the audience. Yes, please.
2 comments from the online attendance. One is a remark. It said, Karsten Kuhn says that you cannot meet the interest of young generation if they don't have benefits from the mineral industry. And also, modern technologies are an essential factor to fascinate them, but the communication must be supported by the PR professionals, especially using social media, so communication again.
Public relations, yes.
And the other comment from John Clifford is that he disagrees with that there are no Tier 1 deposits left in Europe, because recent discoveries such as Kukaru Peki in Serbia, now operated by a Chinese company, and Sakatti in Finland are evidence of the potential. The problem, according to John, is that the lack of exploration investment.
And again, back to also public acceptance, I guess. So just let me ask the panel. I was wondering, we are talking about the future. How do you see mining in 2050? And another question is, because someone once told me, if the mining was developed by one of these high-tech companies like Google or Tesla or something, it might be different. So I don't really know. What do you think? And since you are working on these projects, Guillermo, how is mining in 2050?
Well,
so let's jump forward,
Yeah.
and we'll be here. Of course, I won't be here. I will be probably, if I will be alive, watching online. But but mining in 2050.
It's really hard to say for me, but I guess that in the past, probably the mining entities, mining companies were owning everything, which it makes sense because they were the specialists. But now, all the mining projects or the mining work requires other fields, and we need telecommunication engineers, industrial engineers, other kind of engineers in order to make it safer, easier, more economic valuable. So maybe there are not just one mining company and one miner, but a big group of professional and engineers and other, of course, scientists. More technically, I can see maybe it could be like probably like a video game when you are playing to extract all the minerals, but you don't need to stay just there. But of course, you have made some field research, etc. But you can control everything just for one room. Everything, the vehicles, the extractions, the transportation to the plant. Maybe something like that, but it's really difficult to say.
And that room
Probably I'm wrong.
But that room will be located in the mining site or in India or someplace else?
Could be. Not necessarily just near the mining site. Of course, there should be at least one person controlling that, but it's really difficult to say. Maybe I'm wrong, maybe we are going back to traditional methods, I know.
I mentioned India because Rio Tinto is having their control for maintenance in India, based in India, basically checking that.
Yes.
And Philip, 2050, jumping forward.
It's a complicated one, and being in this high-tech panel here, still I think that it's going to be pretty diverse. So we will have the big and major players who really go into the direction that we are going now, but we will still have some quarries, artisanal mines. So I think it's going to split. It's going to split. The band is opening up. As with any other technology as well, there will be those who kind of feel like left behind. Although artisanal miner might not feel left behind, but they will not take over so much of the technology, and there will be those almost automated and fully integrated mines that we've just been talking about. I think it will go. It's gonna split up a little bit. So we will not be able to take everybody with us, and we need to be aware of this diversity in the industry and in the world, and also in different parts of the world, of course.
Of course. But do you think that these big mining companies, though, these big miners with high tech, they will be having bigger mines or smaller mines, or as Steve presented, these algorithms that are greedy and basically changing the way they will be extracting? Or it's no ideas about that?
Well, I think there will be a change in the way that extraction is going on, but also there it will strongly depend on the type of deposit. So if those small and flexible mining robots like ROBOMINERS, but also the big, somebody mentioned Atlas Copco or Epiroc mobile miner today as the biggest example of a robotic snake. If they are really successful, I think there will be some tendency to go for vein-type deposits underground, following the veins, but then depending on the deposit type, of course, there will be the future ones as well.
Yes. Thanks. Just, Cora, I will be back to you after this round. Kostas, on your perception, mining in 2050 will be accepted with all these new technologies?
Well, I think that, at least in Europe, most of mining will take place underground and not in open pits.
Why?
Because it's much more environmentally friendly, and it's more easy for the people to accept it. And you see, we have in Europe there are many places with fantastic physical natural beauty, and they imagine to keep this in place at the same time to mine underground. It's not the same like mining somewhere in the middle of Africa or in the middle of a dry desert in somewhere in South America or whatever. that is one thing. The other thing is that I would envision, I would like to see the local communities to be more, let's say, to be more engaged with mining, and to have people who are working as technical personnel of the mine, which are highly skilled. So these will be the people who are going to, let's say, maintain the robots. These will be the people who are going to develop new technologies. So yes, big mining will, big companies will still be there. I don't think we'll have big changes there. But at the same time, because even today, in the future, in order to hire someone, there's a big, the main criteria would be from the place where the mine is placed. So imagine to have a community of some thousand people from where highly skilled workers and highly skilled technicians are working with things like artificial intelligence, with robotics, with deep learning, with Internet of Things, and all this stuff. And at the same time, to pass these qualifications to the children who will want to go to study as mining engineers or geologists or electrical engineers or mechanical engineers. You know, for each, I was working in a mine for 10 years somewhere in Norway, and I could see that the people were proud of what they were doing. In each local community, people are feeling very proud about the mine. They feel the mine as their own home.
Yes.
Okay, so this sense of proudness, move it in a different level, not just driving a big truck or a big dumper, but for example, why not developing the robot and
high-tech stuff.
Yeah, high-tech stuff. Yeah.
Okay, thanks, Kostas. That's a problem for the quarry industry. You noticed that? So
yes.
Quarries in 2050.
Wow. Well, it's it's difficult to say what is going to happen. I think that a lot has been done in last 30 years. So I think that a lot of is going to be developed in the next 30. And yeah, I imagine the quarries automatized, digitalized, with a lot of information, big data to process. And what I think is that they are, all the processes will be more optimized and with less energy consumption and
okay.
Yeah.
Small steps, then, not necessarily a big change.
Yes.
Goraz, I noticed that you want to make a question.
Maybe not really a question, but I think that the reasonable scenario for mining in 2050 will be mining on the ocean floor. So there are a huge amount of resources there. Licenses, exploration licenses have already been granted by CBET, International CBET Authority, and there are technological challenges are not too big, and there are already a majority of them have been solved, and the company which will be able to demonstrate that they can actually retrieve these resources on the surface will grant the mining permission instantly. The only problem is political, because United States are not didn't sign this international CBET authority. So yeah, but I think ocean floor is it's the very realistic way to proceed further in 2050.
That will be another step, and I guess your robot is capable of working underground, so it won't be a problem if it is salty water, right?
No, it's not a problem. It's depending on the salinity of the water. But we already tested our robot in oversaturated salt water, in salt brine. But practically that is not the case in seafloor exploration. It's even much more the depth and the pressure what we need to stand. But there are currently existing platforms that are able to stand this pressure and even operate many hours or days or weeks or months on this environment. Yeah, so it's even possible right now. My biggest concern is the political issues and even the environmental issues. So nobody knows what will happen if we are touching those nodules. Nobody knows how will the mining affect on the actual environment and the fishes and all the other living creatures in the ocean bottom. And the biggest problem is that we don't know practically anything about those ecosystems. So it's really hard to estimate what is down there. Even usually what we are telling, that is just a small story, that we know much better the surface of the moon than the surface of the ocean floor. Yeah. So we really don't know what is down there. We need a lot of exploration, a lot of robots, and a lot of time to figure out how it looks like, how it was evolved, and what type of actual mining methods could be used without damaging even that part of our globe.
And I confess I fully subscribe that view. Just let me say before we close that I made a challenge to our audience. And I basically wrote numbers from 1 to 5. And then I was trying to get, and these are surprise questions to our 5 guests. And they accepted to be here with a surprise question. And then I was trying, how can I put the surprise question in my mobile phone and show to the people that they were picking up the right number. And I said, no, I still need to rely on paper and pen. So the question is, which number do you want to get, from 1 to 5? And let's start this final round of questions. You're picking up one number. I'll be reading the question that is behind, and that, of course, you cannot see. Just see the number here. So, Philip, one number, 1 to 5.
I start with 1.
Oh, okay. So the question to you. Do you think that the digital and technological advances displayed in this session will find applications in other sectors behind mining?
Yes. Yes, I cannot specify them directly, but there are many technologies from self-assembly to new sensors, to low-cost sensors, to the use of the low-cost sensors, to strain measurements, to dust measurements, to environmental CO2, whatever we investigate. So yes,
definitely. And I guess this is good news. So that was a fast answer. Thank you. Numbers from 2 to 5, because one has already been taken. Rixie.
3.
Okay, 3. Just let me jump to number 3. And number 3 asks, do you think that we should pay attention to the risks of robotics as presented in science fiction books and films?
Well, if you are considering the 3 laws of robotics, then no. Yeah, but it's depending on what type of robot we are talking about, what type of artificial intelligence and autonomy is behind the robot. But I would say basically there is no type of risk that we are considering during the movies. So they will not evolve that part when they will attacking all the people and start a war. But basically we can even use these kind of robots to mitigate all those risks that are currently existing on any of the other or any of the industrial thing or industrial movements.
Yeah,
so I would say it's other way that we can mitigate the risk and not considering any extra risk on robots.
Because if I understood correctly, some people are afraid of robots.
Because they have a lack of knowledge on robotics.
Okay. So you'll be working with robots without any problems, I would say.
Robots, yes. From our case, it's fine.
The ones that you know, okay. That's a good question. Thank you. So numbers 2, 5, and 4. Costas, which one? 5. So 5. Okay, let me jump to 5. And 5 says, if you had to place a bet, in which technological development would you put your money?
Are you asking me?
Yes. And it's a good question. You are working on the metaverse, on digital twins.
I wouldn't bet on one type of technology. I think the future is on the combination of technologies. And the reason is that we have data from different sources and different data types. So, for example, okay, the field of AI is a huge field. Everybody's talking about it. So I would suggest the combination of AI with robotics. That would be because you have something to think about it and something to do, to take an action on it. So, and of course, let's say, the regulation of these technologies with some kind of ethical code.
This is something that is still missing in many cases.
Yes, it's still basic, and I'm afraid the way that the Western society, not just the Western, I mean, the global society is pointing, is that we have this continuous movement of liberalization, that there should not be any kind of regulation. There should not be any kind of everybody can do whatever he or she thinks to develop things and all this stuff, and there must be some kind of ethical code. And the most difficult thing is that since we're talking about globalized economy, how easy is to make an ethical code for the global itself?
To be accepted by everyone.
To be accepted by everybody, yeah. So
that's a big challenge, huh?
Yeah, it is.
Okay. So you put your money on the fusion of different technologies,
yeah,
artificial intelligence
and
included,
and
robotics. Okay, thank you. So, Guillermo and Jose, I'm afraid we only have the 2 and 4. Which one wants to take which?
What's the first?
Jose, 2 or 4?
Number 2.
Number 2, okay. So number 2 asks, that's interesting. In your perspective, what ethical considerations should guide the development and implementation of artificial intelligence and robotics in mining? Because you just mentioned ethics.
Only in mining?
Yes.
Or because there's a...
Only in mining, I'm afraid.
No,
but you can expand, so feel free to tell us about all that stuff.
Yeah, there's a lot of discussion now in society about the use of artificial intelligence. So, difficult question. Yeah, we have. I think we have to regulate the use of this new technology. But I wouldn't say, there are things that you cannot trespass, but there's too much to think about how, because we want to develop, we want to have an advance, but how can we, or which is the boundary between the ethics? Well, that's difficult. Yeah.
It is. I fully agree with
Yeah.
you. I know that ROBOMINERS has an ethics deliverable, so I guess Claudio might be interested in talking about that later after the session. And Guillermo, I'm afraid 4 is the one left. So the question number 4 asks, will mining be able to ever meet social environmental standards that receive high social license to operate, or high social acceptance?
Well,
so back to social.
They must be, because it's crucial to develop further tasks in mining field. Actually, I think now mining are creating these requirements, social, environmental requirements, because of regulations, also trying to fetch ethics for all the local communities. So I think that we have a good base on that, a good baseline, and maybe we just need to improve it and not forget about that.
Yeah, it's a big challenge ahead.
Yes, it's challenging because it's not an economic benefit, real economic benefit, but it's behind everything.
But
So
I've seen 2, if I may, I've seen 2 clues for that. One is local stakeholders as shareholders, because that's the example from wind farms, and making mines invisible, so underground, right? Yeah. So I guess this might be...
Yep.
Okay. Okay, so thanks everyone for attending the session. I will ask a big applause for our speakers and guests, so thanks a lot. It was great, really good to have you here. And now we are closing this session, giving back the word to Claudio. Claudio, please, you can take my chair. You'll be at the middle.
No, okay, I'm really not the guy of many words. So thank you, everybody. Thank you for the panelists for your contribution and also for your super cool projects. not as cool as
Yes,
ROBOMINERS,
it does,
but-
because you were looking like a mesh on your
No, I'm
face.
kidding. I'm kidding. So, ROBOMINERS is at its end. I understand that many of your projects are just started or halfway like that. So I wish you successful endings, and let's keep in touch for future endeavors.